Hi everyone, this is Bilal. Welcome to tutorial 9 entitled Query Optimization 3 Physical Plan Part 2. So let's grab our set of tools. I want to download lecture 9 slides and practice assignment 9. Okay, also we will use text editor. Calculator, come on. Okay, scientific mode, basic mode. Okay, basic mode, and scratchpad. Okay, we are ready. Okay, lecture 9. So during the previous two tutorials we have been talking about the query optimizer or the query processor, how this part of the database engine processes a query, convert it to the best logical plan, and decide the best set of actions, okay, which is the physical plan, to execute this query. And so tutorial 8 we have learned about how to compute the best logical plan using cost-based optimization, and in tutorial 9 we have learned about the physical plan, and we have been focusing on the join operation. We learned two types of join operations: the zigzag join, the iteration join. So sorry, this should be 7 and this should be 8. Okay, so today in tutorial 9, in this tutorial we will continue the other types of join operations: the merge join, join with an index, and the hash join. And first we have to review the concepts covered by the lecture. Then we have to solve few problems to practice them. Okay, so let's start. So let's learn about the merge join. The idea of the merge join is very interesting. Okay, open. Okay, open it again. Okay, so we want to join two tables, R1 and R2, and we have a common column C. The items in the common column in both tables are sorted ascending order. Okay, so we start at I and J. Next we compare to the corresponding two items. 5 is less than 10, and since the list of items, this list of numbers, is sorted and increasing order, so we can skip 5 uh, to find 10, okay, to find 10 in R2, and we may not find 10, that's fine. So now we stand here at 20, 10 less than 20, so let's increment I. So now we stand at 20 and 20. We enter a nested loop and we create a new temporary variable called jj, and we set jj to 2, and we leave j as it is. Okay, so 20 and 20, join them, increment jj. 20 and 20, join them, increment jj. 30 and 20, they are not the same, so exit and destroy jj and increment the I. So back again to j equal to, now 20 and 20, enter nested loop, create jj again. 20 and 20, join them, increment the jj. 20 and 20, join them, increment the jj. 30 and 20, they are not the same, stop the nested loop, increment I. So I stands here, and j still stands at the second item. Okay, so 20 and 30, they are not the same, and 20 less than 30, so let's increment j, so we may find 30 later on. 20 and 30 again, increment j. 30 and 30, so j stands here right now at 4. Now 30 and 30, we have to enter nested loop, jj equal 4. 30 and 30, join them and go to the next item in R2. Okay, 30 and 30, join them, then go to the next item in R2. They are not the same. Okay, so we have to increment I, and we can stop here, okay, because R1, relation R1 is exhausted. So this is the basic idea beyond the merge join, and here's the pseudocode. It's pretty simple. If the two items, the current two items, are the same, then we enter a nested loop to output all of the possible similar pairs. Okay, else we increment the iterator of the relation with the less value. Okay, so if R2 is less than R1, we increment j. If R1 is less than R2, we increment I. And if they are the same, we enter this nested loop and we output the current pair, then we increment the jj until the current items are not equal, then we increment I, and we proceed with the same logic. So what is the cost in terms of the number of input-output operations to perform the merge join? Okay, if we have relation R1 and R2 and they are sorted and they are contiguous, so each block will cost us a single input-output operation. Okay, so the only cost is to load the blocks of R1 and R2, and remember they are sorted. Okay, the only cost is to load them and merge join them in the random access memory. So if R1 has 1000 blocks and R2 has 500 blocks, the cost of bringing them into the memory is 1500 input-output operations. However, if they are not sorted, Okay, in case both relations R1 and R2 are not sorted, we have to sort them. So what is the cost of the sort? Okay, new discard. So here's our hard disk. And here's the blocks of a relation. Okay. So we need to sort these. So we have to load each block in the memory. So this is the first input-output operation. Okay. Then we sort the tuples inside each block. Then we write them back to the hard disk, the sorted ones. This is second I/O. Then we need to sort across the blocks and merge the overlapping blocks, so we have to load them again in the memory. This is the third I/O. After that we have to write the sorted blocks again to the hard disk, so this is the fourth I/O. And if we want to merge join the blocks of both relations R1 and R2, we have to load the blocks into the memory for the third time. This would be the fifth input-output operation. So the cost of merge join unsorted relations is 5 IOs times the total number of blocks if they are contiguous. Okay. Here's come the second join with an index. So join with an index works as follows. We have to create an index for let's say relation R2, and for each tuple or row that belongs to R1 we have to search in the index, and then we join the output pairs. So let's assume that we want to join R2 and R1, and we have R1.c index and it fits in memory, and R2 is contiguous unsorted. Okay, so we are gonna search inside R1.c index using the values stored in R2. So if R2 has 500 blocks and it's contiguous, it will cost us 500 IOs. Then for each value in R2 we will search R1.c. Since R1.c, according to this assumption, fits in memory and already exists in memory, it will cost us 0 input-output operations. If we found a match, okay, then we have to read the corresponding R1 tuple, since the index contains the keys and pointers to the corresponding tuples. The index doesn't carry the tuples itself, so we have to load the matching tuple that belongs to R1 to join it with the current value from R2. This will cost us extra 1 input-output operation. So we have 3 cases. The first one is primary key, foreign key. Second one duplicates, and the third one we have duplicates with no stats. So let's see them. The first case is that we have R1.c index and column R1.c, column C in relation R1 is a primary key, and R2.c is a foreign key. So based on this piece of information, we can assume that for each value in R2.c there is a matching, okay, one match in R1.c. So reading R2 blocks, okay, R2 is contiguous as we have just said during the previous slides. So loading 500 blocks costs costs us 500 input-out operations, plus each block of these holds 10 tuples. So we have in total 5,000 tuples in R2, and for each one of them there is a matching, and for each matching it costs us 1 IO. So 500 to read R2 plus 5,000 to load the 5,000 matching tuples to join them costs us extra 5,000 IOs. In total we have 5,500 input-output operations. The second case, R2C references R1.C, however R1.C contain duplicates. Given the following statistics, okay, R1 has 10,000 tuples, 5,000 of them are unique, so we can assume that each tuple is duplicated twice. So for each value in R2 we will find 2 matches. So we can modify the cost of the previous case as follows: 500 to read R2, 5,000 for each one of these 5,000 there is 2 matches, and for each match it costs us extra input-output operation. So in total we have 10,500. The third case is when R2C references R1.C, and R1.C contains duplicates, however we don't have statistics. Okay, so we know the data type of the column are R1.C and R2.C, so we can guess the domain, and of course we know the total number of tuples in R1. So what is the chance that when we search for a value of R2 we will find it in the 10,000 tuples of R1 and not the other values of the 1 million values in this domain? The chance is 10,000 over 1 million, which is 1 over 100, and this is the expected number. Okay, this is not an exact number. So again, 500 plus 5,000, for each one of these 5,000 we have a chance of 1 over 100. Okay, and we use this method only if we have no stats. So here is a summary of the 3 cases. Okay, what if the index doesn't fit in memory? Well, it depends. If we are searching in the loaded part of the index, the loaded part in memory, we are good. And if we hit the part of the index that is not loaded and it's located on the hard disk, then this is not good, because this will cost us extra 1 IO for each block index. So we have to estimate or predict or expect the cost. Okay, so if R1C index is 201 blocks, then we will keep the root node and 99 leaf nodes in the memory. So if we hit one of these 99 leaf nodes, it will cost us 0, and the chance that we hit one of these 99 leaf nodes is 99 over 200, like the chance of getting number 1 when you roll a dice, 1 over 6, 1 over all possible options. Okay, and if we hit one of the 101 blocks stored on the disk, it will cost us extra 1 IO, and the chance is 101 over 200. So the expected cost is 0.5. So we have to add extra 0.5 to the IO intended to load the matching tuple. This is the overhead to access the index that is not loaded inside the memory. The last type of join we are gonna learn in this course is the hash join. The idea beyond the hash join is very creative, since we want to join relation R1 and R2 and there is a common column, and R1 and R2 are sorted. Okay, so we will hash the R1 tuples into a certain number of buckets, and we will hash R2 into H buckets. Then we can match the tuples in the corresponding buckets only. Okay, let me visualize it to understand what I am saying, what I'm trying to say. Okay, here is R1 and here is R2. There is common column between them, column Y. So let's hash the tuples of R1 based on column Y. Okay, so R1 dot Y hash table, and let's do the same for R2. Let's hash the tuples of R2 based on column Y, which exists here. Also R2 dot Y hash table. 4 1 2 3 4. Okay, here are the keys: key 0 1 2 3, key 0 1 2 3. Since both relations are sorted, okay, and we created these two hash tables based on the same column, the common column Y. We will find that the corresponding buckets contains the matching tuples. Okay, so instead of trying to searching for a certain value in R1, trying to search for it in the whole relation R2, the searching operation become exclusive only on the corresponding buckets. So the cost will be 3 for reading R1 and reading R2 to hash both relations, then reading the hashed buckets of R1 and R2 to join them. Please, you have to go back to the lecture to understand the theory, the issue of caching that made us multiply by 3, not by 4 or by another factor. Okay. So now we are ready to we have refreshed your memories, and we are ready to solve a few problems about these concepts to practice them. Okay, so let's bring assignment 9. The first problem says, consider two relations R and S. The number of blocks in relation R is 800,000, and the number of blocks in relation S is 300,000, and you have 1001 memory pages available to be used as a swap area. Okay, now he asks us to compute the minimum number of input-output operations needed to join these two relations using block nested loop join. He means the iteration join, so pay much attention to the terminologies. And second time, compute the minimum input-output of operations if we are gonna use the merge join and the hash join. You can assume that the hash function evenly distributes key across buckets. Justify your results by showing the input-output cost estimation for each join method. Okay, so the first one is we are gonna use iteration join, and we have to use these memory blocks. Okay, so here's the hard disk. We have 800 memory blocks, 800,000 memory blocks for relation R, and for relation S 300,000 memory blocks. And here is our RAM, and we have 1001. Okay, so I will use 1000 of these blocks to load the smaller relation S, 1000 block by 1000 block, and I will use this extra block to pass over or iterate over all blocks of R to join it with the resident 1000 blocks of S. So we have here 1000 blocks of S. They will cost us 1000 IOs, plus passing over the 800,000 blocks of relation R, 800,000 blocks, and we will do this for how many? So we can ask ourselves how many thousands are there in relation S. Okay, 300,000 over 1000. This gives us the number of chunks. Let's check our answer. Correct. And this will cost us 240 million input-output operations. A very huge number. Okay. The merge join, as we have just said during the previous synopsis over the lecture, to compute the merge join, and he gives us this hint: the relations are not sorted, so we need to sort them. Sorting each block for each relation will cost us 4 IOs. Loading both relations after the sorting will cost us extra IO per block. So let's multiply 5 times the total number of blocks of both relations R and S. So 5 times 800,000 plus 300,000. This gives us 5 million input-output operation. And in this case, the merge join is much better than the iteration join. The last one is the hash join. According to the lecture, the rules stated in the lecture slides, we multiply the total number of blocks by 3. So 3 times 800,000 plus 300,000 gives us 3 million input-output operations, and the hash join is the lowest cost of all of them. Okay, good. Let's solve question number 2. Question number 2 asks us to compute the cost in terms of the number of input-output operations to perform these joins. Okay, given the following statistics, we have two relations R and S. T of R equals 8,000, T of S equals 3,000. Okay, the number of tuples for relation R and the number of tuples for relation S. The number of blocks of relation R 800. The number of blocks of relation S 300. The number of distinct values for relation R, okay, in relation R for attribute A is 100 distinct values. The number of distinct values for relation S, okay, for attribute A is 3000. And we have 101 available memory blocks to compute the following joins. Okay, compute the minimum number of input-output operations needed to join these two relations. Okay, let's perform the merge join. Okay, if they are sorted and contiguous, so the only cost is to load the blocks of relation R and S into memory and merge join them. So the cost will be 800 plus 300 input-output operations since they are contiguous, so each block costs us only a single input-output. So in total, the first merge join will cost us 1100 input-output operations. The second merge is also merge join, okay, given that the data are not sorted and still contiguous. Okay, if they are not sorted, we multiply the total number of blocks since they are contiguous by 5. So the cost will be 5 times, okay, 800 plus 300. 5 times 1100 equals 5500 input-output operations. Okay, let's solve number 5. The hash join. Okay, if the tables are hashed and contiguous, if they are already hashed and contiguous, so the cost is to bring the blocks into memory to merge the hashed corresponding buckets or pages. Okay, so the cost again will be 800 blocks since they are contiguous plus 300 blocks. Okay, one input-output operation for each block. So in total, just like the first merge join of the sorted relations, 1100 input-output operations. In case they are not hashed and contiguous, so we'll multiply the total number of blocks by 3. So it will be 3 times 800 plus 300. 3 times 1001 gets us 3300 input-output operations. And 4 and 5, let's solve 4 and 5. Okay, index join. Okay, the first one. Okay, the first one. Use index join if only s dot a is indexed, okay, and the index fits in memory, and s is not clustered over a. So we have an index over a, and we have these stats, the total number of tuples in S and the number of distinct values in S. Okay, so so the cost will be the needed input-output operations to load relation R, since we are gonna search in S.A index. So we need to load R in memory, and this index already exists in memory. So the number of blocks in of relation R is 800. So this costs us 800 to load relation R. Okay, and relation R, okay, each one of these blocks holds or carries 10 tuples, so we have 8000 tuples. We are gonna search for 8000 tuples. For each one we will have how many matches we don't know, but we are searching inside S relation S index. Okay, so we have to use the number of distinct values and the total number of tuples. Okay, so let's divide the total number of tuples over the total number of distinct values. So this gives us 1. So for each one of these 8000, there is one matching, and we will do an extra IO. So we have in total 8800 IOs. And let's do the opposite. Okay, let's create an index for relation R instead. So the answer is 8800. Okay, so let's do the opposite. We have an index for relation R, so we have to load relation S in memory, and S has 300 blocks, so this costs us 300 IOs plus Thus, we have to search for each tuple in S, and S has 3000 tuple, and for each one we have to compute how many matches are gonna be there. Okay, so we are searching in relation R index. Okay, so we have to divide the total number of tuples by the total number of distinct values for column or attribute A, which is 100. So let's grab our calculator. 8000 over 100, 8000 over 100, 80 times 3000, 240,000 plus 300, 240,000 and 300. Okay, 240,000 and 300, correct. So we have solved all the problems listed in practice assignment 9. I guess we are finished. See you in the next tutorial. In the next tutorial we will talk about a new concept. Sorry. Grab. Okay. Lecture 10. By this tutorial we are finished with the query processor, and we are gonna transfer to these 4 components: the transaction manager, the log manager, the buffer manager, and the recovery manager. Okay, we will focus on these highlighted 3 components in the next tutorial, tutorial number 10, about the logging techniques and database management systems. Thank you so much. See you and goodbye.